So, we will study magnetic properties of solids. Magnetic properties of solid. So, to study the property of a solid, we need to apply external parameter and see the response of the material to that parameter. So, you have seen that say if I take a piece of material so, I want to study the thermal properties of this material. So, I have to apply that thermal energy. So, and its temperature means temperature of the system will change and response of this material to temperature. So, that gives us the thermal properties of the material in terms of some parameter. So, that is basically specific heat or thermal heat capacity or this conduction of this thermal conduction, right. In case of electric properties of material of this piece of material. So, if I want to study, so I have to apply electric field and see the parameters like conductivity, resistivity, right, mobility, density of states or density of carriers, etc. So, similarly, if I want to study the magnetic property, so I have to apply magnetic field and see the response of this magnetic field, response of this material to the magnetic field in terms of some parameter, which basically tells us about the magnetic property of the material. So, which are those parameters? Which are those parameters in case of magnetic property? So, these parameters one is magnetization, So, magnetization of this material is defined by the magnetic moment per unit volume. So, this material is having the magnetic moment if it has. So, all material have magnetic moment. So, two types of magnetic moments are there. One is induced magnetic moment, or dipole moment, induced magnetic dipole moment, magnetic dipole moment, and another is permanent magnetic dipole moment. So, we tell magnetic dipole moment because another kind of dipole moment are there. So, that is electrical dipole moment. Okay. So, that we will see in case of dielectric material. So, in magnetic material, so this there are dipole moments. It can be induced dipole moment or permanent dipole moment, right. So, whatever the dipole moment, magnetic dipole moment, so total dipole moment of this of a piece of material, if it is m and then divide by the volume of this material, so that will give the magnetization. So, we write in using the capital M, right. So, varying the value of this magnetic moment magnetization or the value of this magnetization as a function of magnetic field, as a function of temperature. So, that tells about the properties of this material, magnetic material, right. So, another parameter we use, that is susceptibility. As I told, this magnetization varies as a function of magnetic field. So, the susceptibility is basically defined as the magnetization per unit magnetic field. Okay. So, for a particular magnetic field, you will get magnetization, value of magnetization. Now, for unit field, what will be the magnetization? That is the definition of susceptibility. Okay, we write using chi. Third parameter is basically permeability. So, that is really we write by mu. So, mu is used for this symbol is used for many cases, the refractive index, this permeability for dipole moment. Okay. So, just you should not be confused, just wherever we are using. So, you have to know the context, and you have to think that what is that, either permeability or refractive index or dipole moment. So, the symbol mu. So, now what is mu? So, to explain that, I need to tell about the difference between the magnetic field H and the magnetic induction B. Okay. So, both are field. So, what is magnetic field? Basically, this magnetic field is we express in terms of lines of force, magnetic lines of force, okay, per unit area. So, per unit area, through per unit area, what is the number of lines of force? So, that is the magnetic field. So, these basically we tell these lines of force, we tell in terms of flux, magnetic flux. Okay. So, magnetic flux means magnetic lines of force, and this flux per unit area, so that is the magnetic field, okay. Lines of force per unit area, that is the magnetic field. Now, in air, if there is no material, especially there is no magnetic material, air or vacuum or this non-magnetic material, there whatever we applied external magnetic field, that is H. Okay. But in presence of magnetic field, in presence of magnetic field, sorry, in presence of magnetic material in a magnetic field. So, in this magnetic field, if we place a material, if it is non-magnetic material, so there is no problem, lines of force is like this. So, density will not change, density of magnetic this flux per unit area, it will not change, it will be like this. But if it is magnetic material, then this lines of force change, because this magnetic material, it will be magnetized by this magnetic field, and so this magnetic material, it will behave like a magnet. That means, this magnetic material itself will generate magnetic field, So, now you will have these two field, one is your external field H, and another is field due to this magnet. It will behave like a magnet which will generate magnetic field. So, now inside of this material, whatever total field, this lines of force for this external field, and some lines of force for this magnet. So, this will, so if it is say it is magnet, means it will behave, this surface is say south pole and then this north pole, then lines of force generally it comes out from this north pole, okay, and enter into the south pole, and then from south pole to north pole. So, here direction is this, here direction is this. Okay. So, you have external magnetic field, Okay. Now, here you can see there is outside the direction of this external magnetic field and this magnetic field due to this magnetic material. So, they are in opposite direction, outside, opposite direction, but inside it is in same direction. So, as if they will outside they will cancel this external magnetic field, or it will reduce the strength of this external magnetic field. So, what will happen inside of the material, this now lines of force will be more, and outside of this material lines of force will be less. Okay. So, now this inside whatever this field you will, total field you will get, that is expressed by B, magnetic induction, magnetic flux density inside the material is B, magnetic flux density outside the material, that will be expressed by B A. Okay. A, I mean this air, okay, magnetic flux in air. So, because this is no more, it is H, it will change because this magnet will affect the magnetic field, it will affect the field outside of this material. Of course, inside of the material it will change. So, in presence of magnetic field, presence of magnetic material in air, we use this term B A, and that B A equal to, we write it has relation with H. So, that is H is, we write mu 0 H, and B inside of this material we write B equal to mu H. Okay. So, this mu is basically called the permeability. This mu is called the permeability, right. So, mu 0 is the permeability of air or vacuum or non-magnetic material, and mu is the permeability of this magnetic material. Okay. So, so basically this field will be enhanced due to this factor, or it will be reduced due to this factor, depending on whether mu is less than 1, or mu is equal to 1, or mu is greater than 1. Okay. So, this mu is the permeability, and that is written with respect to air's permeability. So, it is written mu 0 into mu r H. So, mu r is called the relative permeability. So, with respect to the air, what is the value of the permeability of this material. Okay. So, mu r is the relative one, and mu 0 is the absolute permeability of the air. Okay. So, so there are some material where it is seen that this B is reduced, mu is less than 1. Okay. So, that type of material is called diamagnetic material. Means inside the material these lines of force, number of lines of force are reduced. Okay. So, we can think that there is a magnetic material, there is a material. Okay. So, lines of force, basically lines of force, this whatever your its external magnetic field, say as if there is a repulsion, okay, there is a repulsion. Okay. So, here lines of force, whatever the initial external magnetic field, whatever the lines of force, density of lines of force are there, now it is reduced. Okay. So, this type of material is called the diamagnetic material. So, and superconductor is a perfectly diamagnetic, it shows the perfectly diamagnetic property, superconductor, that we will see. So, this is the case, and this and in case of this mu equal to 1. So, there is a change of the field inside the material. So, this is basically non-magnetic material, non-magnetic material. Okay. And when mu is greater than 1, then density of these lines of force inside the material will be higher, right. So, it will be just opposite, as if this magnetic material attracted these lines of force inside the material. So, whatever, so it will be, so what is supposed to go by this, so it will enter into the material, so it will enter into the material. Like this. Okay. So, inside of this material, the line density of lines of force will be increased. So, mu is greater than 1. So, this magnetic flux density will be higher, B will be higher than H. Okay. So, then this is called the paramagnetic material. Paramagnetic material or ferromagnetic material. Right. Now, this if mu is just slightly greater than 1, then it is paramagnetic. If mu is very greater than 1, so then it is ferromagnetic, right. And now, in ferromagnetic there are other type of material, magnetic material. So, that is when mu is very greater than 1. So, this it can be ferromagnetic or it can be antiferromagnetic, or it can be ferrimagnetic. Okay. So, that will explain. So, you forget this mu equal to 1 non-magnetic material, you forget that part. Okay. So, when mu is less than 1, so that is diamagnetic. When mu is greater than 1, so this paramagnetic, ferromagnetic, antiferromagnetic. Okay. So, as I told that this magnetic material have two types of dipole moment. One is induced dipole moment, another is permanent dipole moment, and that is the origin of this magnetization. Okay. That is the origin of the magnetism. So, this diamagnetic material, which material shows the diamagnetic property. So, that is basically the material which are not having, which will show the induced dipole moment. Okay. And this material may have permanent dipole moment or may not have permanent dipole moment. So, it does not matter. Okay. If metal have permanent dipole moment, it may have induced dipole moment. So, it will show the paramagnetic property. okay, diamagnetic property if it does not have the permanent dipole moment, but it has the induced dipole moment. So, then also it will show the diamagnetic property. But in this case, this property of the material is shown by those materials which are having permanent dipole moment, Okay. So, permanent dipole moment is compulsory to get this type of property, ferromagnetic property or paramagnetic property, antiferromagnetic property or ferrimagnetic property. So, this for this permanent permanent dipole moment is responsible, okay. And this diamagnetic property, that is the induced dipole moment, is responsible. Okay. So, now these material are classified into two category. One is based on the induced dipole moment. So, that is the diamagnetic property, and another is based on the permanent dipole moment. So, then that is in that category again there is a division. So, paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic, right. So, this is the broad classification of the magnetic material, and now we will study the individual one. So, but before that let me find out the relation among this parameter. There is a relation among this. So, B, what we got, B equal to mu H, mu can be written mu 0 mu r H. Okay. Just if I add mu 0 H and subtract mu 0 H, okay, then I can write B equal to, I can write mu 0 H plus mu 0 then H plus mu 0 H, and then this I can write mu 0 H and then mu r minus 1, right. This I can write. So, this mu 0 H plus mu 0, if I write mu 0 m. So, mu 0 H. So, B has two parts, as I mentioned, one is coming from this external magnetic field, another is coming from the internal this magnetic material, right. So, this mu 0 H, that is coming from the that is the contribution from the external magnetic field in here, okay, plus this additional from magnetic material. So, magnetic material is having the magnetic moment, and magnetic moment gives the magnetic field, right. So, that means magnetization gives the magnetic field, magnetic moment gives the magnetic field. So, from magnetic material whatever the contribution in field is coming, so that is we can write mu 0 m. Okay. So, then this equal to then mu 0 H plus m. Okay. So, then we are getting M equal to, we are getting M equal to H external magnetic field whatever we have applied, okay, mu r minus 1, mu r minus 1, right. So, chi equal to then m by h is nothing but mu r minus 1, right. So, chi is related with this, how it is related with the permeability, that is the relation, okay. And this magnetization, how it is related with the magnetic field and the permeability. So, this is the relation between this mu m and chi, mu m and chi, right, mu m and chi, okay, this is the relation. So, from here you can also see that if I in presence of magnetic field, so I can write B by B A, right, B by B A equal to mu by mu 0 equal to mu 0 mu r, so equal to mu r, okay, equal to mu r. So, these are the relation of this magnetic parameters, okay. So, this are very useful for studying the magnetic property of the solid, okay. So, then we will discuss about this origin of this magnetism. So, that is coming from induced dipole moment as well as the permanent dipole moment. So, we will discuss in next class. So, I will stop here. Thank you for your kind attention.